welcome to our
collab video.
Okay, so we're going to first talk about atomic radius. So this is periodicity. And so as you can see from this diagram here, as you move to the left, the atomic radius increases. And that makes sense because on this side with these nonmetals here, there's a higher effective nuclear charge, which means that there are more protons per energy level, so that they're really pulling those electrons to them. It's like a really strong attraction. And then also here, the atomic radius increases as you go down the periodic table, which again also makes sense because there are more energy levels, so it's harder. There can be some shielding, so it's harder to pull those electrons to the nucleus. So yeah.
So ionization energy. Ionization energy increases as you go this way on the periodic table and increases as you go up on the periodic table. So basically ionization energy means removing an electron. So like I talked about in the last video, if you watched it, there are the PEZ diagrams where you can have the first ionization energy and second ionization energy. But for example, there's we are just referring to the first ionization energy in this case because the easier to remove an electron from a metal, it's much easier to remove an electron from a metal like sodium because sodium commonly has a +1 charge. But it would be really hard to remove an electron from fluorine because it wants to have a -1 charge. But by removing an electron, you're making it more positive. So it's a lot harder to remove an electron from an element on this side of the periodic table versus this side because the metals tend to have that positive charge. So either one or two lone electrons in a shell makes it easier to remove an electron than from a full shell. So electronegativity. So it's not the same thing as electron affinity, but it has the same trend, and I'll talk about that in the next slide. So this says increasing electron affinity, but it also has to do with electronegativity. So it increases as you go this way on the periodic table and increases as you go up on the periodic table. So for example, this is the best, I think, method to describe it. So fluorine has a really strong electronegativity is the attraction, the ability for an element to attract an electron. So fluorine has a very high electronegativity because it has the highest electronegativity because it has a very strong attraction to an electron because it usually has a -1 charge. And that's similar to all of these halogens. So the difference between electronegativity and electron affinity is electronegativity, like I said before, is the ability for a substance to attract an electron. So like I said, fluorine's the most electronegative. And electron affinity is the ability for a substance to gain an electron. So as you can see, they have the same trend, but they have slightly different definitions, so don't mix those up.
Okay, so now we're just going to talk about a misconception with electron configurations. So chromium and copper are two big exceptions to your typical electron configuration rules. So both of these transition metals will have this. Let's look at the diagram. So we have the expected configurations up here. This is what you would probably expect. And then, but down here, this is what actually happens. So this is like Hund's rule because it's more stable for an electron to have unpaired electrons. That's what happens here. So for chromium, you can see that it has a 4s1, which is probably pretty surprising. And then similarly copper, copper wants to have this last one filled. It doesn't want just one that's unpaired. So it also has 4s1. So that's just a common misconception with chromium and copper. That's all. Thank you.